Hey everybody, welcome to another session of MCAT Max, and my name is Andy. Today we'll be going through um, an AAMC style chemistry physics passage, and um, all the passages that we go through are available on jackwestin.com for free, and we'll put the link in the YouTube description. So if you ever want to maybe read through the passage or try it out yourself before coming back to this video, feel free to. Okay, so I'll just kind of briefly go through the passage. There are 6 questions, and walk you kind of through how I would analyze the passage, kind of break it down and make it understandable for myself, and how I would go through the passage and also the figures, and kind of understand the reaction pathways, because I know organic chemistry can be kind of confusing with all the functional groups and everything that's going on. So we'll do that first, and then we'll go to the questions, and I'll just show you all my strategies that I use to kind of narrow down choices and find the correct answer. All right, so let's get started. So the passage begins with alginate, a natural polysaccharide, forms hydrogels via ionic or covalent cross-linking. Ionic cross-linking involves multivalent cations binding to COOH groups on alginate chains, but it often yields hydrogels with weak mechanical properties due to rapid chelation. Covalent cross-linking, however, offers a solution with slower, controlled reactions that result in robust hydrogels. Alginate hydrogels cross-linked covalently with adipic acid dihydrazide, or AAD, have gained prominence in biomedical applications. So I don't know about you, but when I finish reading a passage out loud, I understand nothing of what I just read. So I'll go back and kind of read it in my own head and try to see what was important, right? Okay, so the main thing here is alginate, right? So this is a polysaccharide, right? So this is a polymer. So it's essentially a really big compound that's made up of a lot of smaller subunits, which in this case is sugars. So it's just a lot of sugars bonded together, and they're forming these things called hydrogels. And really, hydrogels are a mixture of usually a polysaccharide or other type of polymer with water, right? So that's why you get the hydro part of it. And what it does is mixing these polysaccharides with water kind of makes it expand and create this gel-like structure. And so it's saying it can do this through ionic or covalent cross-linking. So it can either do ionic cross-linking. So this is essentially linking together different alginate chains, and does that through multivalent cations. Okay. And this kind of makes sense, right? Because cations are positive, right? So we have these positive things binding to COOH groups. So those would be carboxylic acid groups, which are, if you may recall from Orgo, those are negatively charged groups. So it makes sense that we have a positive thing binding to a negative thing. And that would obviously make an ionic bond. But it often yields hydrogels with weak mechanical properties, okay? And then covalent cross-linking is another way. It has slower, more controlled reactions. And so one thing we can use to do this covalent cross-linking is this AAD thing. All right, so going to the next paragraph. The gelation kinetics of alginate chains can be customized for specific applications. For example, swift gelation suits hemostatic dressings, while gradual gelation is preferable for cell encapsulation. Recently, the latter has been utilized for topological adhesion between existing hydrogels. And then we're saying, okay, we can introduce an aqueous mixture of alginate chains, AAD crosslinker, so this was the one that we talked about before, and coupling agents like blah, 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 EDC and NHS. And if we add all of these things together, right, we create this whole big mixture, we can form a covalent network that has really good adhesion. So a lot of this I feel like we won't really need, right? It's just, okay, making sure we know, the main thing here is just adhesion, right? How can we improve the adhesion? And we're like, okay, we can bring in not just AAD, but we can bring in this thing called EDC and NHS. I feel like that's the main point here. Um, okay, so covalently cross-linking allogeneic chains using AAD, EDC, and NHS involves three main reactions. Okay, this seems important. So COOH, the carboxylic acid group on the allogeneic chain, reacts with EDC to form some type of urea intermediate. And then this intermediate reacts with NHS, creating a stable NHS ester intermediate and releasing urea. And then this thing goes on to react with two more allogeneic chains to establish crosslinks. This cross-linking pattern spreads, forming a 3D network, and the initial reaction is slower than subsequent ones, with rate constants K1, K2, K3 having various magnitudes. So already I'm stopping right here. I feel like this could be really good fodder for a future question about rate constants. What's the rate limiting step? Right? Whenever you read through these passages, over time you'll find out, oh, they're definitely going to come back to this later, and this is definitely stands out as one of those sentences. And going on to the figure, we can kind of see the figure is kind of showing this last paragraph in graphical form, right? So we said here we have three reactions, right? And it basically just goes through what are these three reactions, right? So the first one is the COOH. The COOH on allogenate reacts with EDC to form an acylisourea intermediate. Wow. But it all checks out, right? So this is just corresponding to the first step. And then this intermediate goes on to, right, so these two compounds are the same. This intermediate reacts with NHS, creating a stable NHS ester intermediate and releasing urea. And the NHS ester intermediate, we have two of them, then it reacts with AAD to form crosslinks. Okay, so again, it's just going through each of these three reactions, and I feel like I think after that step, after just reading through that and going through the figure, and just convincing myself that I understand why they put this figure in, I'll just move on to the questions, right? Because there is limited time for the passage, so we want to make sure to get to this. Okay, so the diagram below depicts one crosslink between two allogeneic chains using AAD molecules. Which of the functional groups are represented by the letter Y? And they filled a triangle indicated with circles respectively. So when I first read this question, I was really confused because I was like, what is this letter Y? And apparently it's this thing right here, right? So these Y things are sticking out, which I feel like just isn't obvious enough because you could just mistake these for simple branches. And then this thing was really confusing. It filled a triangle indicated with circles, which turns out to be this arrow. I'm really confused about why they didn't just say arrow, but usually on the actual AMC exam or the MCAT exam, I'll be more clearly denoted. But now that we figured out one part of the problem, right? So we know what the letter Y is, it's this thing, and we know what the filler triangle is. We're trying to find out which functional groups do those represent. Okay, so we kind of need to decode this figure. What is this figure showing? It's essentially showing cross-linking, right? We see these these three chains kind of being connected by these arrows. So what's being cross-linked here? Right, it's allogenate. That's the main thing we're doing. That's the whole point of the passage. We're trying to cross-link allogenate chains to make these hydrogels, to make these polymer networks. So we know these long things are allogenate, and so essentially to find out why, we just need to find out what is sticking out of allogenate. What does allogenate use, right, to connect with these arrows? So essentially the arrows can connect the Y parts of the allogenate and then connect the whole allogenate chain together. Okay, so what is on the allogenate? That would be the letter Y, right? Going back to the figure of the reaction, we know it's the COOH group, right? The carboxylic acid group. That's what's on the allogenate. That's what is involved in the cross-linking. And for further evidence, right, we see ionic cross-linking involves multivalent cations binding to COOH groups on allogenate chains. So knowing that, I feel like the first answer should be COOH, right? But let's move on to the fuel triangle. So this is what's connecting the COOHs together, right? So this triangle connects to the COOH of alginate and the COOH of another alginate. So what's that? So we're looking at here which connector molecule, right? We're looking at AAD. So we need to figure out what's the structure of AAD. So going down here, what's the structure of AAD? AAD is this molecule. So what things can it use to connect to the COOH, right? So it's the NH2 here, right? So NH2, when it binds to COOH, this is a really classic biochemical kind of synthesis reaction. You get an amide bond. That's the main thing you get. And this is what you use to kind of build proteins, build peptides, and yeah, it's just another term for it is like a condensation reaction, where an amine, right, and a COH come together. Actually, I can make this more clear. So if we have R and H2, and that reacts with a carboxylic acid group on another molecule, you'll get R N C O, right? And this is your amide bond. Or amide bond, depending on how you pronounce it. So knowing that though, we're pretty confident it should be COOH and NH2. And because those two can create such a strong peptide or amide bond, you can connect these alginate chains together, right? Awesome. So going on to the next question, based on the passage, which of the following will least likely cross-link alginate? And I'm just looking at here, where did we even talk about these metals or these positive charges coming from? I see sodium, I see calcium, aluminum, iron, and there's only one place that I remember talking about cations and talking about positive charges, right? So that was at the very beginning, and let me make my pen a little bit thinner. So ionic cross-linking involves multivalent cations binding to COOH groups. So which of the following does not fit that description of a multivalent cation, right? Right, so it's multivalent. So multivalent, right, just from the name means it's multiple charges. So anything that does not have a multiple charge would not be likely to cross-link alginate. And because of that, A should be the correct answer because this is 2 charges, this is 3 charges, and this is 3 charges. But sodium, because it's in that first group, only loses 1 electron to form Na+. So this one is an example of something that's very simple to answer only if you kind of know where to look in the passage, right? Because it's not immediately obvious just from the answer choices how we're going to go about this, but if you were to carefully, closely read the passage and you spotted this multivalent, that's just like the key, because once you see that multivalent, you're like 99% sure you're going to get it right? So it's just a matter of looking at that, which I think kind of, it's an important lesson that carries on to the chemistry passage and really to the cars section as well, is that oftentimes it's a scavenger hunt of just finding that one sentence or one phrase that has that answer. And once you find that, you're pretty much very confident you've got the right one. But again, close reading is key. Okay, so question 3. Scientists want to determine the rate order of the 3-step alginate cross-linking reaction, right? So this is, I mean, I may have been a little bit biased because I did go through the questions, but this question is talking about that one sentence I pointed out earlier, right? Now we're discussing the rate order. And specifically, we want to know, how can we find the rate order? Or I guess if we want to find the rate order, how do we do it? We would keep the alginate concentration the same and measure what? So the first thing to understand about the rate order is, right, whenever we talk about rate order, we always want to focus on the rate limiting step. So I think that's like the first step to tackle. Which of these 3 reactions is the rate limiting step? And the sentence kind of gives it away, right? If the initial reaction is slower, the slowest step is always the rate limiting step. So this reaction A is the rate limiting step. And now that we know we have to focus on reaction A, how would we manipulate it to find out more info? They're saying we should keep the alginate concentration the same, right? So we should keep this the same and measure I would say we should keep this the same and measure this and change this, right? Because this is like our control. We're not changing this at all. This is our like independent variable where we want to change, and then we're going to find out what happens to this. So we're just basically creating a really small scientific study. Um, and so knowing that, that would kind of lead us to, we want to measure the concentration of O-acetylsuria intermediate when this is doubled, right? And this kind of takes care of this question, but I kind of do want to go further and say like, okay, so what would be some expected results, right? And um, the main thing here is like, for example, what if we actually did this experiment and we saw that the concentration of O-acetylsuria intermediate doubled when EDC concentration doubled? What would be the rate order, right? And the rate order of that would just be 1, because if the reactants double, so let's say if this goes up by ×2 and this goes up by ×2, then the rate order is 1, because it's kind of, it's a one-to-one relationship. If this doubles, this also doubles. Another scenario that you might see is we doubled the reactants by, we multiply it by 2, and the products actually go up by 4. So what would the rate order be for that? That would actually be a rate order of 2, because you're essentially multiplying these two things together to create a 4 times increase. We can also see the rate go up by 8, and then I think you can get the point here. Then the rate order would be 3. So the main thing here is we always have to keep this thing steady, because we can't compare it if we change both of them at the same time. If we keep one of these reactants the same, then we can manipulate the other reactant, see what the effect is, and then use that to find out what power are we raising it to, and that will give us the rate order. Awesome. All right, so question 4. Which of the following is more similar to the bond formed between NHS ester intermediates and AAD? Okay, so NHS ester intermediates, where did we see that? That was right here. And AAD. Okay, so it's essentially this reaction, right? We're saying these two things come together, what type of bond do they form? All right, so what type of bond is this? So we have, so this part stays the same. And then this thing comes together, right? So, okay, so essentially what we're looking at here is, because this is also the other side, which is kind of complicated, but we have two alginate things coming together. But this kind of just goes back to before, right? What bond are we forming when we're connecting the two alginate chains together? Pretty much as simple as that. And you can even see here, this little thing right here is kind of that bond that's formed. It's not present in either one, but it's present in the end product. And as I mentioned before, this is a perfect example of an amide bond, or an amide bond, which is also a peptide bond. It's the main thing that makes up the peptides. And it makes sense, right? Because we always learn amino acids have NH2 groups, they have COOH groups. So it makes sense that when amino acids come together to form proteins, to form peptides, they make that peptide bond and that amide bond. Cool. Which of the functional groups is not present in O intermediate? All right, so this one was actually a little bit tricky, right? So O-acetylsuria intermediate is this thing right here, right? So it should be pretty simple. Which of the following functional groups is not present? Ester. Do I see an ester? I see an ester right here, right? So ester is that. So you can have stuff on either side, but it's that COO, right? So whenever you see COO, that is an ester. We definitely see that, so therefore it's not A. Do we see an ether? So an ether would be O with two things in either end. Now, I would be careful, because if you said this was an ether, you're not exactly correct, because it's actually part of the ester. So usually we say it's not really an ether, but it's just an ester, because the ester is kind of, it is the whole thing, and it takes precedence. An ether would be if there was no double bond to the O, and if it was just C bonding to something else, and that would be an ether, right? So we don't really see an ether, right? So I would keep this, I would still keep choice B, and then move on to choice C. So do we see an acid anhydride? So an acid anhydride would actually be O, C, O. So it has two carbonyl groups kind of out to the side of a central oxygen. And I really don't see that either as well. So I don't see a C either. And I also don't see an alcohol, which is an OH group, right? I don't see it here. But obviously we can't choose B, C, and D. So there must be a missing kind of key to this question, which is this alginate group, right? So we need to know that this alginate group kind of represents a whole, almost another molecule that is not shown in the figure. And what makes up the alginate group, right? So the alginate is a polysaccharide. We said polysaccharides were polymers of sugars. So just a bunch of sugars that are kind of linked end to end. And using that, we can kind of further reason that we would have an alcohol group, actually, because the alginate, because the sugars in the alginate, right? Remember when we have, sugars, we always have these, OH groups kind of hanging off of here, OH group here, OH group here. That was what made up a sugar, right? So this is, for example, what glucose or ribose or fructose might look like. And a lot of these bonded together, I remember these glycosidic bonds. Those are the things that connect these sugars together. Those are what make up alginate. So an alginate is just this repeated over and over again. And from this figure, you can kind of see we do have an alcohol group, and we actually do have an ether group, because remember, glycosidic linkages are all ether linkages. They're all ether bonds. And so the answer should be C, right? So this is the only thing that's not present in alginate or in this molecular structure here. And it kind of makes sense too, right? Why would you have an acid anhydride? And if you go back to orgo and remember, acid anhydrides are actually very reactive. So they usually are not stable in water, and they're just very rarely seen kind of in biochemical or biological reactions, especially as part of a hydrogel, just because they're not stable enough, because they would actually prefer to break apart, right? So this would kind of prefer to break apart and maybe form a carboxylic acid. So because of that, we can eliminate B and D and arrive at the answer C. Okay. Last question. Which of the graphs may reflect the reaction kinetics of the three-step cross-linking of alginates? Okay. So this kind of goes back again to the idea of what is the rate limiting step. Which again, the sentence was really very key to answering 2 of your 6 questions, right? And we know that the rate limiting step was reaction A. So it was this one. And what else does being the rate limiting step tell us? It tells us that it's the slowest step, which means it should have the highest activation energy, which we represent by EA. Okay, so it takes the most energy for reaction A to get going. And how can we translate that into a graph? So I see answer choice A here. We can see here, right? So this is reaction 1, this is reaction 2, reaction 3. They each have their own activation energies. And here, obviously, in answer choice A, reaction 1 is not the highest, so we can kind of eliminate that. B, yeah, it could be the highest, right? C is not the highest, and D, it is the highest, right? So immediately I'm like, okay, I don't think it's A, I don't think it's C. It could be B, and it could be D. So what kind of differentiates the 2 things here? It's very tricky, right? So I see products here, reactants here and products here. I mean, this is just, why would you ever have products in the front, right? Just doesn't make sense. Another thing we can kind of use is, how do we for sure know they're not just tricking us, is kind of comparing the initial, the beginning energy and the final energy, right? So we see here, both of them involve a drop in energy. So what does a drop in energy mean? A drop in energy means we're making something that's more stable. That's a very big takeaway, is that whenever you see the final line or the final reaction kind of ending up lower than the initial part, it means there's a drop in free energy and the products are more stable. So in this reaction, which one is more stable? Is it going to be the reactants or is it going to be the products? And the key thing to know here is that whenever you have a condensation reaction, or it can also, I guess a subset or a type of condensation reaction would be peptide bond formation. Whenever you have some type of thing that's forming a bond and usually connecting two things together, that final connected synthesized product is going to be at a lower energy. It's going to be more stable than the two things separate, right? So whenever, to put it simply, whenever we have a condensation reaction like this, the products are always going to be more stable and have less energy than the reactants. So we know that the correct order should be going from reactants to products because we're going down in free energy and we're making something that's more stable. So with that in mind, and also knowing that this first reaction should have the highest activation energy, we should know that D is the correct answer here. All right, so I've probably spent maybe 5 times more than the allotted time for this passage, but I really wanted to kind of go through it really thoroughly, explain all of my thought processes, and hopefully kind of give you a window into how a perfect scorer might be able to analyze the passage. And one thing I really like to use again is making sure you really search long and hard in the passage for those key sentences that often really just give away the answer, right? It's just a matter of finding it, and once you find it, it just has that key that will let you just pretty much answer the question correctly all the time. I would say that, and I would also say, be liberal with your use of process of elimination like I did here. And once you eliminate, for example, A and C, I just never look at them again, right? So just focus or narrow down your search to B and D and then just go from there. Really saves a lot of time and make sure you're not being distracted by other answers that can never be correct. Yeah, so that's pretty much all I have. Remember to check out Jack Westin for more free passages. Also check out our socials or visit our website mcatmax.org for more resources. And yeah, we'll be actually posting a lot more frequently on our TikTok too. So look out for some more questions of the day in the future. And with that, I will see you all at another time. Thanks for stopping by.